In 2025, the red planet witnessed something extraordinary. From the blackness of interstellar space, the object known as 3I divided by Atlas swept past Mars at impossible speed. Astronomers already knew it was no ordinary comet. Its hyperbolic orbit proved it came from another star. But no one expected what happened when it entered Mars's neighborhood. For a brief moment, orbiters circling the planet recorded strange fluctuations in the thin Martian atmosphere. Dust storms shifted in ways that defied prediction. A faint glow appeared in the skies above the red desert, as if the planet itself had been brushed by an unseen hand. And then, just as quickly, it was gone, the visitor racing onward, leaving scientists to wonder whether Mars had just experienced a cosmic encounter that could alter it forever. Was it merely the natural shedding of gases from an alien comet? Or something far stranger, a controlled maneuver, a burst of radiation, a fragment of material never before seen in our solar system? To stand on the Martian surface that night would have been to witness the sky come alive with a light no human eye had ever seen. 3I divided by Atlas did not collide with Mars, but its passage was close enough to leave a mark not on the land, but on our imagination. A reminder that the universe still holds the power to terrify, even without violence, simply by showing us how small and unprepared we are when the stars send visitors our way. It began as a faint point of light, just another entry in the nightly harvest of data gathered by automated telescopes. On July 1st, 2025, the Atlas survey in Chile flagged something unusual. A smudge moving against the stars with a velocity that did not belong to any object bound to our Sunday. Within hours, astronomers confirmed what the orbital calculations whispered. This was an interstellar traveler, the third ever detected, and by far the most mysterious. They called it 3I divided by Atlas, a designation that marked it forever as a wanderer from beyond. But this was not merely another curiosity for the catalogs. Its path told a far stranger story. Unlike the slow drift of a typical comet or asteroid, this object was screaming through space at more than 200,000 kilometers per hour, a speed that no natural body from our solar system could maintain. And more startling still, its trajectory threaded the inner planets with uncanny precision, steering close enough to the orbit of Mars to brush the edge of cosmic danger. Mars has always been a mirror for our imagination, the god of war in mythology, the frontier of exploration in science. Its skies are thin, its deserts red, and its history long. Yet, in that summer of 2025, Mars became something else, a stage for a passing terror. As 3I divided by Atlas drew near, orbiters circling the red planet recorded subtle disturbances. Dust devils twisted in unpredicted directions. The faint atmosphere, so tenuous it can barely hold on to clouds, seemed to ripple as though struck by an invisible wave. And high above, a glow appeared weak, fleeting, but real enough to make scientists wonder if the planet had just been brushed by an alien exhalation. To a human standing on that barren surface, the sight would have been unforgettable. Imagine the sky above Gale Crater, thin and pale, the stars sharper than anywhere on Earth. Then imagine a new light moving too fast, glowing with a strange hue, trailing a haze of gases not native to this solar system. No sound would have reached your ears, but you would feel the weight of history pressing down. The knowledge that a piece of another star system had just passed overhead. For scientists, the terror lay not in collision, but in uncertainty. What happens when a body carrying unknown chemistry, forged in conditions alien to our sun, brushes so near to a world we one day hope to colonize? Could it seed the Martian soil with molecules that shift its future? Could radiation bursts sterilize regions already fragile and cold? Or could it pass silently, doing nothing but reminding us how fragile our models are when confronted with the reality of the cosmos? The truth is that no one knew. Even as the James Webb Space Telescope stared into the void, even as radar beams from Earth tried to paint its shape, the answers slipped away. 3I divided by Atlas was too fast, too strange, too fleeting. By the time its glow had faded from the Martian sky, it was already gone, racing outward past the orbit of Jupiter, leaving behind only data, questions, and a profound sense of unease. And so Mars became a witness, silent, unblinking to a passage both terrifying and sublime. The visitor near Mars reminded us that the solar system is not a closed system. It is open to the galaxy, exposed to wanderers that arrive without warning, without invitation. Some come quietly, some leave scars of mystery. And 3I divided by Atlas. In that brief encounter did something more. It unsettled our certainty. It proved that even in an age of satellites and supercomputers, the universe can still surprise us, still frighten us, simply by passing close enough to let us know we are not alone. On the evening of July 1st, 2025, a quiet revolution began with a single telescope image. At the Cerro Tololo Observatory in Chile, one of the robotic survey stations of the Atlas network was sweeping the sky as it always did, clicking exposures every 30 seconds, mapping moving specks of light across the heavens. For most nights, the software flagged nothing remarkable. Countless asteroids trace their slow, predictable arcs. Satellites leave bright streaks that must be filtered out. Cosmic rays strike detectors and mimic false stars. But this night was different. The algorithm caught something faint, moving faster than any near-Earth asteroid should. At first, it was only a smudge, barely distinguishable from noise. Yet, when the images were stacked and compared, the truth emerged. This object shifted against the background stars with a pace that could not be ignored. Its motion was too rapid for a main belt asteroid, too unusual for a comet from the Oort cloud. Within minutes, the data were transmitted to the Minor Planet Center in Massachusetts, where orbital calculations confirmed what the Chilean computers had already suspected. The trajectory was not bound to our Sunday. Astronomers felt a familiar chill. The orbital eccentricity, a measure of how stretched an orbit is, came back greater than 1. That single number told the story. This was an interstellar object. A visitor that had entered our solar system from elsewhere in the galaxy, destined never to return. It was only the third such body ever found, following Oumuamua in 2017 and Borisov in 2019. But unlike those predecessors, this one was brighter, faster, and already far closer than anyone expected. In the hours that followed, observatories around the world scrambled to confirm the discovery. Hawaii's Pan-STARRS array caught it skimming across the constellation Microscopium. The Zwicky Transient Facility in California added further detections. 3 independent confirmations left no doubt. Something extraordinary was racing inward. By sunrise in the Americas, astronomers were already whispering the designation that would mark the history books 3I divided by Atlas. Detection is often described as a quiet act of measurement, but for those involved, it carried a pulse of awe. Each line of numbers represented an object older than Earth itself, ejected from some alien nursery and flung across light years to cross our path. The light that fell onto those detectors had left its surface only minutes earlier, but the story it carried stretched back billions of years. To detect such a thing was to catch history in mid-stride. As orbital calculations refined, the discovery turned unsettling. The trajectory showed a close approach not to Earth, but to Mars. In just 3 months, the visitor would sweep through the inner solar system, passing the red planet at a distance that in cosmic terms was frighteningly near. Mars would not be struck, but the geometry was precise enough to make astronomers pause. Was this coincidence, or was there more to this interstellar wanderer than chance? The news spread quietly at first, shared in professional networks, embargoed from the press until certainty was achieved. Yet, among the scientists watching the data, there was a sense of something almost theatrical in the timing. For decades we had scanned the skies, waiting for another Oumuamua. Now, just as our fleet of Mars orbiters and rovers reached their technological maturity, the universe had delivered an interstellar guest that would pass directly within their view. The moment of detection was not dramatic in the way cinema imagines, no flashing alarms, no sudden exclamations. It was quiet. A dim point of light on a monitor, a number greater than 1 in a spreadsheet. Yet in that silence lay the seed of everything that followed. The debates, the sleepless nights, the speculation about origins and intentions. From that single smudge of light, humanity was thrust into a new chapter of cosmic awareness. The detection of 3I divided by Atlas was, in truth, the detection of our own vulnerability. It reminded us that the universe does not ask permission before sending its messengers. It simply delivers them, silently, into our sky. The numbers told the truth long before the headlines did. When astronomers plotted the orbit of the object that would come to be called 3I divided by Atlas, one value stood out: its eccentricity. Anything born in our solar system, asteroids, comets, even the most chaotic fragments, travels on paths shaped by the sun's gravity. Their orbits are ellipses, closed loops that may stretch into centuries but always return. Even the long-period comets that dive in from the distant Oort cloud eventually circle back. But the eccentricity of 3I divided by Atlas was not slightly above 1. It was far beyond. This meant something profound. The object was not bound to our sun at all. Its orbit was hyperbolic, a curve that never closes, a line that enters and then leaves, destined to vanish into the galactic dark. In the precise language of celestial mechanics, this made it an outsider, a visitor that had crossed the invisible frontier of our solar system only once, never to repeat the journey. To astronomers, that was both thrilling and unsettling. Hyperbolic orbits are not unknown. Occasionally, a comet that passes too close to Jupiter can be flung outward, accelerated enough to escape forever. But such expulsions leave a signature in their velocity. They move just fast enough to slip away. 3I divided by Atlas was different. Its approach speed, known as the hyperbolic excess velocity, was about 25 kilometers per second relative to the Sunday. That is faster than any ejection our planets could provide. This was not a native comet thrown out of the nest. This was a wanderer from another star system, carrying with it the chemistry and history of an alien world. Astronomers traced its path backward through space, attempting to find its birthplace. But interstellar dynamics are messy. Over millions of years, tiny tugs from passing stars and molecular clouds scramble trajectories beyond recognition. The further back they looked, the blurrier the trail became, until it was no more than a probability cloud smeared across the Milky Way. Somewhere out there, perhaps dozens of light years away, a planetary system had shed this fragment. And after a journey longer than human civilization, it had arrived at Mars's doorstep. The word hyperbolic carries with it more than just mathematics. It suggests exaggeration, the language of fear and awe. And in this case, it was fitting. For a world that has always seen itself as the center of the story, to confront a body that came from elsewhere was a reminder of how small we are. 3I divided by Atlas was not just another comet. It was an emissary of the galaxy itself. When telescopes studied its light, they saw hints of strangeness. The glow was brighter than expected for its size. The coma, the thin envelope of gas surrounding the nucleus, appeared asymmetric, as if venting in unusual directions. Radar reflections were faint and oddly smooth, suggesting surfaces unlike the jagged profiles of ordinary asteroids. And all the while, its hyperbolic trajectory carried it relentlessly forward. unbothered by planetary gravity, immune to capture. It was here on its own terms, and it would leave the same way. For scientists, the hyperbolic orbit was both a gift and a curse. A gift because it proved beyond doubt that we were seeing a true interstellar object, not a local imposter. A curse because its path meant we would only have one chance to study it. Unlike comets that return after decades or centuries, 3I divided by Atlas would sweep past once and then vanish forever into the dark between stars. A hyperbolic stranger is, by definition, temporary. It cannot stay. It cannot be held. The most we can do is watch, measure, and imagine what stories it carries from its long voyage. And as 3I divided by Atlas moved past Mars, streaking across the sky of a world we have always dreamed of reaching, we were reminded that our solar system is not isolated. It is part of a larger community of stars and debris, where strangers may arrive at any moment, unannounced. 3I divided by Atlas came to us not as a friend or a foe, but as a reminder. The galaxy is alive with motion, and we are only one stop on its endless map. Speed is a familiar concept on Earth. We measure it in kilometers per hour, in meters per second, in miles per hour. We know the rush of a car on a highway, the thrust of a jet crossing the sky, even the thundering escape velocity of a rocket breaking free from gravity. But none of these prepare us for the velocity of an interstellar visitor like 3I divided by Atlas. When astronomers first calculated its motion, the numbers seemed almost unreal. Over 200,000 kilometers per hour. That is more than 55 kilometers every single second. To put this in perspective, in the time it takes you to blink, 3I divided by Atlas had traveled farther than the distance between many cities. It was moving so quickly that no planet, no gravitational embrace in our solar system could ever hold it. Its path was one way only, an arrow drawn straight through our neighborhood, already aimed at the far side of the galaxy. Such speed is not an accident. In the vast emptiness between stars, there are no engines, no pilots, no deliberate acceleration. The momentum of an interstellar object is a fossil, a record of the forces that shaped it long ago. Perhaps it was flung outward by a giant planet circling a distant sun, or hurled into the void by a close encounter with a passing star. Once launched, there is nothing to slow it down. Space offers no friction. Across millions of years, even across billions, that initial push carries it endlessly forward. By the time we detect it, the story of its departure is ancient history. And yet, speed this great is not just an abstract number, it changes how we perceive the visitor. A normal comet drifting in from the Oort cloud can be tracked for years. We can predict its return centuries ahead. With 3I divided by Atlas, there was no luxury of time. From the moment of discovery to its closest approach to Mars, only a handful of months passed. For astronomers, it was a race against motion itself, a desperate attempt to learn everything possible before the object slipped away forever. The speed also altered the encounter with Mars. At 200,000 kilometers per hour, no atmosphere, no magnetic field, no surface feature of the red planet could truly touch it. Instead, it was like a bullet passing through smoke. The thin Martian air rippled faintly, disturbed for an instant before returning to stillness. Dust storms shifted, then settled. Any material shed by the comet's surface would have streamed past in a heartbeat, scattering along a line too faint to follow. To stand beneath such a passage would not be to watch an object drift across the sky, but to witness a flash of movement too quick to comprehend. For the human mind, there is a limit to what speed means. We can picture a car overtaking another. We can imagine a plane flying overhead. But when velocity exceeds the scale of our daily experience by thousands of times, it becomes something else. A force of nature, almost beyond imagination. Astronomers called 3I divided by Atlas a hyperbolic stranger, but it was also a stranger in time, here and gone before our instruments could fully adjust. What terrified some was not the danger of collision, but the lesson in humility. We live in a solar system we often treat as secure, predictable, mapped. Yet here was proof that the galaxy is filled with wanderers moving at speeds we cannot match, cannot chase, cannot even intercept with our most powerful rockets. For all our progress, for all our machines orbiting Earth and Mars, the truth was laid bare. We are slow, fragile, and small. Speed beyond comprehension is not just about numbers on a page. It is about perspective. 3I divided by Atlas reminded us that the universe runs on scales of motion and time that dwarf our own. It crossed the gulf of interstellar space, swept past Mars in a blur, and continued into the dark, leaving behind only a memory, a glimpse of what true cosmic velocity looks like. On October 3, 2025, Mars became the unwilling host of a celestial drama. The interstellar traveler, known as 3I divided by Atlas, swept past the red planet at a distance closer than any of its moons, moving at a velocity so great that the encounter lasted only hours. And yet, in that short span, Mars was touched by something it had not experienced in billions of years, a brush with a body born beyond our solar system. The orbit predicted it precisely. Astronomers had traced the hyperbolic path of 3I divided by Atlas, watching as it threaded the space between Earth and Mars. On that day, the red world and the interstellar visitor shared a patch of cosmic stage, their paths converging in a geometry that seemed almost deliberate. From Earth, telescopes caught only a faint glow in the constellation Virgo. But from Mars, if human eyes had been there to see it, the sight would have been otherworldly. Picture standing on the rim of Valles Marineris, the Grand Canyon that scars nearly a quarter of the planet's circumference. The sky above is butterscotch-colored, thin with dust, the stars sharp against the void. Then, in the stillness of that alien air, a new light appears brighter than the background stars, moving too quickly to be mistaken for any natural satellite. Within minutes, it grows, trailing a veil of gas illuminated by the sun, a ghostly plume against the Martian sky. For a brief moment, the planet's barren landscape is bathed in a glow not of Earth, not of Mars, but of a visitor from the galaxy beyond. Mars orbiters bore silent witness. The Mars Reconnaissance Orbiter, with its powerful high-rise camera, tracked the object as it streaked past. The thin Martian atmosphere rippled faintly, registering disturbances too subtle for the human eye, but clear enough in the instruments. Dust devils shifted direction. A storm that had been expected to dissipate instead swelled, as though stirred by an invisible tide. In the data logs, faint fluctuations in pressure and temperature told the story of a planet nudged, however gently, by an alien presence. For planetary scientists, the encounter raised unsettling questions. Could particles shed from 3I divided by Atlas settle into the Martian soil? Could alien ices, rich in carbon dioxide and exotic compounds, seed the frozen regolith with chemistry not native to our solar system? And if so, what might that mean for the fragile search for life on Mars? Some feared contamination, that the visitor might sterilize regions with bursts of radiation or scatter toxins across the dust. Others dreamed of the opposite, that fragments might enrich Mars, adding the building blocks of life where before there was none. Yet, for all the speculation, the reality was humbling in its simplicity. 3I divided by Atlas passed too quickly, too far from the surface for any dramatic transformation. Mars remained as it had been, cold, silent, ancient, and yet the encounter left an imprint, not measured in chemistry or geology, but in human imagination. From Earth, we have always looked to Mars as a second home. We picture domes and cities rising on its plains, astronauts leaving footprints in its dust. To see it brushed by an interstellar wanderer was to see those dreams reframed in cosmic context. Mars is not only our neighbor, it is also a stage in a galactic story, vulnerable to the same random encounters that shape every world. The red planet encounter did not bring catastrophe nor salvation, but it brought perspective. For a few hours in October 2025, Mars was no longer just a barren desert orbiting our Sunday. It was part of a larger drama, a world visited by a stranger from another star, illuminated not by human ambition, but by the silent passage of a body that reminded us how wide the universe truly is. When 3I divided by Atlas swept past Mars in October 2025, no human eyes were there to see it. The planet remained uninhabited, silent, its surface rovers limited to ground-level horizons. But orbiting high above the dusty deserts, a small fleet of robotic witnesses stood ready. Their instruments became the first interplanetary observers of an interstellar object, recording data that humans on Earth could only dream of. The Mars Reconnaissance Orbiter, MRO, had been circling the red planet since 2006. Its high-rise camera, capable of resolving objects the size of a coffee table on the surface, turned its gaze outward for a different kind of target. For years it had mapped canyons and dust storms. But on that October night, it tracked a streak of light cutting across the Martian sky. The images it returned were not beautiful in the way photographs are. They were fragments, faint lines, slightly blurred, against star fields. But in those lines was history. The first close-range record of a traveler from another star passing a world not our own. Other orbiters joined the vigil. MAVEN, designed to study the Martian atmosphere, noticed subtle disturbances as 3I divided by Atlas swept by. Instruments detected ripples in the upper layers of the thin air. Not a shockwave, not a collision, but a whisper of altered conditions. Tiny changes in charged particles hinted that the visitor's coma, its faint halo of gas, had interacted with Mars's fragile exosphere. For a planet with no global magnetic field, such interactions mattered. Even brief, they revealed how vulnerable Mars is to cosmic encounters. The European Space Agency's Trace Gas Orbiter contributed another layer of detail. Built to detect methane and other trace molecules, it scanned the space around Mars during the encounter. Its spectrometers picked up faint signatures not usually present in the Martian environment. Traces of carbon dioxide and exotic carbon compounds drifting in the high atmosphere. Whether they came directly from 3I divided by Atlas or were simply stirred from the planet's own reserves by the disturbance, no one could be sure. But the anomaly was real, a chemical fingerprint of the passing stranger. From Earth, the data trickled in with delay. Scientists hunched over their consoles, translating the raw numbers into stories. The orbiters, each with its own limited perspective, painted a fragmented but powerful picture. 3I divided by Atlas had not simply passed by unnoticed. It had brushed against Mars in ways too delicate to see but too precise to ignore. Had there been astronauts on Mars, they might have seen a faint glow in the sky, perhaps even a veil of gas lit by sunlight. But even without human witnesses, the orbiters gave us something more permanent. Hard evidence. Not speculation, not blurry, ground-based telescopic images, but real measurements taken from within the sphere of the encounter. For planetary science, it was the closest we had ever come to touching an interstellar visitor. The significance extended beyond Mars. For the first time, humanity observed an object from another star, not just from Earth, but from another planet. Mars became a relay, a vantage point that expanded our cosmic reach. The orbiter's glimpses reminded us that our robotic explorers are more than scouts for future colonists. They are our eyes and ears in places where chance and history intersect in ways we cannot predict. The data were imperfect, as all such encounters are. The orbiters had not been built for this. Their cameras were tuned to map surfaces, their spectrometers designed for thin atmospheres, their sensors for dust and storms. Yet, by adapting and aiming outward, they captured something irreplaceable: the subtle signs of a galactic wanderer brushing past a world that has always symbolized our future. Mars orbiters caught a glimpse of 3I divided by Atlas, not enough to solve its mysteries, but enough to confirm its presence, its reality, its effect. For a brief moment, the red planet became the closest stage for a cosmic drama billions of years in the making. And through the lenses of our machines, we were there too, watching from afar, humbled by the knowledge that the universe had allowed us a front-row seat to a visitor we may never fully understand. Mars has always been a world of dust. Its atmosphere is so thin that it cannot hold clouds of water vapor like Earth's. Yet it can lift fine grains of iron-rich sand high into the sky and keep them suspended for weeks. Entire hemispheres have vanished beneath storms so vast that they darken the sun and silence rovers on the surface. Dust is the heartbeat of Mars, shaping its seasons, sculpting its landforms, and filling its sky with haze. But in October 2025, when 3I divided by Atlas swept past the red planet, the dust seemed to move in ways that puzzled scientists. For weeks before the encounter, models had predicted the behavior of regional storms. Instruments aboard the Mars Reconnaissance Orbiter and MAVEN tracked the usual patterns: gusts rising from the southern highlands, dust devils twisting in valles marineris, thin veils spreading across the equator. Then came the night of the encounter. In the data that followed, something was different. The storms changed course. Thin curtains of dust rippled where no wind should have been. Some vortices collapsed, while others expanded into chaotic plumes. The changes were subtle, not visible to the naked eye from Earth, but undeniable in the measurements. Scientists argued, was this coincidence, or had the interstellar visitor left its shadow across Mars's atmosphere? The possibility was both thrilling and unsettling. A comet's coma, the cloud of gas and particles released by solar heating, can stretch millions of kilometers. At its closest approach, 3I divided by ATLAS passed within 29 million kilometers of Mars, close enough that some of its expelled material could have brushed the planet's outer atmosphere. Even a faint interaction might stir turbulence in air so fragile. Mars, with no magnetic field to shield it, stood exposed to whatever energy and particles streamed from the passing stranger. Imagine standing on the Martian surface beneath such a sky. The horizon glows pink with scattered light. A storm is gathering, its tendrils crawling across the plains. Then, for reasons unseen, the wind shifts. Dust rises higher, curling in unexpected directions, as though the planet itself is listening to something far above. To human eyes, the changes would appear ordinary, just another restless day on Mars. But behind the numbers, behind the instrument's steady gaze, the pattern whispers of an encounter with the unknown. Some scientists compared the anomalies to a tide. Just as Earth's oceans rise and fall under the pull of the moon, perhaps Mars's dust responded faintly to the invisible currents of a cometary coma passing by. Others suggested electrical effects, that ionized gases from 3I divided by Atlas brushed the exosphere and changed how dust grains charged and clumped together. Neither explanation could be proven. Both fit the data. The greatest mystery lay in what was left behind. Weeks after the passage, dust storms still carried unusual signatures. Their frequencies and durations did not match the seasonal averages. It was as if the encounter had nudged the system slightly off balance, a subtle change that could ripple through the climate for months. Perhaps it was nothing more than coincidence, a planet behaving as it always has. Or perhaps, in that moment, Mars had recorded its first brush with a traveler from another star. For the scientists watching from Earth, the dust became a messenger. It told them that the encounter was not abstract, not distant. It was real, measurable, something that touched a world we hope one day to walk upon. And though no storm grew large enough to endanger orbiters or rovers, the lesson was sobering. Mars is not isolated from the galaxy's wanderers. It can be stirred by forces far beyond its skies. Dust storm shadows became the lasting image of the event, not dramatic, not catastrophic, but quietly profound. A reminder that even the thinnest air can carry the signature of an interstellar passage. A reminder that sometimes the only evidence of a cosmic visitor lies in the smallest shifts of dust on a barren world, recorded by silent machines circling above. When 3I divided by Atlas swept through the inner solar system, its presence was felt in ways more subtle than dust or light. For a brief moment in October 2025, astronomers asked a question that seemed almost unthinkable. Could the passing of this interstellar wanderer have altered the path of Mars itself? At first glance, the idea sounds impossible. Mars is a planet with a mass of more than 6 trillion kilograms, locked into orbit around the Sun for billions of years. No comet or asteroid, no matter how large, could ever hope to shift such a giant. And yet, the laws of gravity are impartial. Every object pulls on every other, no matter the difference in size. The question was not whether 3I divided by Atlas tugged on Mars, it certainly did. The question was whether that tug was strong enough to matter. The numbers tell a reassuring story. The estimated nucleus of 3I divided by Atlas was only a few kilometers wide at most, perhaps smaller. Compared to Mars, it was a grain of sand beside a mountain. Even at its closest approach, tens of millions of kilometers separated the two worlds. The gravitational pull across that distance was tiny, so small that no spacecraft could detect it directly. Mars did not lurch in its orbit. The red planet did not wobble from its course. For all practical purposes, it continued circling the Sun as though nothing had happened. And yet, some astronomers lingered on the thought experiment. Imagine for a moment if the geometry had been slightly different, if 3I divided by Atlas had been 10 times larger, or if it had passed 10 times closer. Mars might have experienced a measurable nudge, a subtle change in its orbital period or eccentricity. Such a change would not be catastrophic, but it could accumulate over time, altering seasons, shifting climates, perhaps even reshaping the planet's long-term history. In that sense, the gravity game was a reminder of how delicate planetary motion truly is, balanced across billions of years, but vulnerable to rare encounters. There is also the matter of perspective. To us, an orbital shift measured in fractions of a millimeter per year seems meaningless. But to the universe, such differences accumulate. Planetary dynamics are sensitive to the smallest changes, just as a coin balanced on its edge can be tipped by the faintest breath. Mars may not have shifted this time, but the mere possibility forces us to reckon with the randomness of celestial mechanics. Even without a measurable tug, the encounter taught scientists something profound. By modeling the gravitational interactions of 3I divided by Atlas and Mars, astronomers tested the limits of their tools. Could orbiters detect minuscule changes in their own paths as the comet passed? Could Doppler signals from spacecraft reveal the faintest echoes of interstellar gravity? The answer, for now, was no. But the exercise sharpened our methods, preparing us for the day when a larger or closer visitor might come. Some theorists extended the question further. If Mars itself did not shift, could its fragile dust storms, its tenuous atmosphere, its tiny moons have felt the difference more acutely? Phobos and Deimos, each less than 30 kilometers across, are far more vulnerable to perturbations. A shift of even a few centimeters in their orbits could matter for future explorers, changing tides of dust across the Martian sky. While no such effect was detected, the thought reminded us of how gravitational ripples can cascade across a planetary system. Subtle, but real. In the end, Mars remained unchanged. Its orbit, its seasons, its long march around the Sun continued as always. But for scientists and dreamers alike, the passing of 3I divided by Atlas raised the curtain on a deeper truth. Gravity binds us all from the smallest pebble to the largest planet, from the faintest star to the galaxy itself. Even a tiny interstellar visitor racing through the solar system plays its part in that universal dance. Mars did not shift its path in any measurable way. And yet, in a poetic sense, something did change. Our awareness shifted. Our understanding deepened. For a moment, we were reminded that orbits are not eternal lines carved in stone. They are fragile balances, vulnerable to chance, to encounters, to the unseen hands of wanderers who pass through uninvited. When 3I divided by Atlas first revealed itself, astronomers instinctively reached for familiar categories. To call it a comet was the easiest choice. It showed activity, a faint coma, gas escaping as sunlight warmed its surface. It glowed with a diffuse halo that suggested ices turning to vapor. In every textbook sense, that made it comet-like. And yet, as the weeks passed and instruments focused on this new arrival, the label began to feel inadequate. Most comets in our solar system follow a predictable script. They emerge from the Kuiper belt or the distant Oort cloud, slowly brightening as they near the sunday. Their chemistry is dominated by water ice. Their tails sweep outward under the push of solar radiation, and their comas follow patterns we understand from centuries of observation. They are not simple, but they are familiar. We can model their behavior with a confidence that comes only from repetition. 3I divided by Atlas refused to follow the script. Its coma was larger than expected for an object its size, far larger, in fact, than any known model predicted. Instead of the strong water vapor signature astronomers anticipated, it displayed an unusual dominance of carbon dioxide. Its ratios of gases seemed inverted, as though the very recipe of its ices had been written in a different language. Where our comets were rich in water, this one was strangely dry. Where our comets shed dust in predictable streams, this one seemed to vent in patterns that shifted and scattered without warning. Even its brightness puzzled observers. Based on size estimates, it should have been faint, barely visible to powerful telescopes. Yet it shone more strongly than expected, suggesting a surface or structure that reflected sunlight unusually well. Some speculated that its crust might be smoother than those of typical comets, or that hidden fragments within the coma scattered light in ways that fooled our instruments. The truth remained elusive. And then there was the shape. Radar echoes hinted at a nucleus, perhaps only a few kilometers wide, but its coma extended across hundreds of thousands of kilometers, dwarfing anything we might expect from an ordinary comet. To imagine something so small, producing such an enormous cloud, was to confront physics at the edge of what we understood. Was it fragmenting into pieces too faint to detect? Was it releasing exotic ices that expanded far more efficiently than water vapor? Each explanation stretched the limits of comet science. Comparisons to its predecessors only deepened the mystery. Oumuamua, the first confirmed interstellar visitor, showed no coma at all, a dry shard that accelerated away under forces we still debate. Borisov, the second, looked like a textbook comet, its chemistry unusual, but its behavior largely familiar. 3I divided by Atlas seemed to combine contradictions. Visibly active, yet chemically bizarre. Comet-like in form, yet alien in function. It was neither wholly like Borisov, nor wholly like Oumuamua. It was something in between, or perhaps something entirely new. For planetary scientists, this was both frustrating and exhilarating. Each observation chipped away at the illusion of certainty. We had thought comets were simple enough. Dirty snowballs, fragile, and temporary. But here was an object from another star system, telling us that the diversity of comets across the galaxy might be far greater than we ever imagined. If 3I divided by Atlas was typical of some other stellar nursery, then our solar system's icy wanderers might represent only a narrow slice of a much larger cosmic spectrum. To call it a comet was not wrong, but it was incomplete. 3I divided by Atlas was like no other we had ever seen. It blurred categories, broke models, and forced us to reconsider what a comet truly is. Perhaps, in the end, it was not a comet in the way we define them, but something older, stranger, and more mysterious. A messenger carrying not only gases and dust, but the quiet reminder that the universe resists our neat definitions. For comets, outgassing is a familiar story. As the sun's warmth penetrates their icy surfaces, frozen materials transform directly into vapor, streaming into space, and creating the ghostly comas and tails we see. Water is usually the main actor, with carbon monoxide and carbon dioxide playing supporting roles. Astronomers have studied this process for centuries, refining models that can predict how much gas a comet should shed at a given distance from the sunday. It is a cycle we thought we understood. But then came 3I divided by Atlas, and the story no longer made sense. When the James Webb Space Telescope turned its powerful infrared eyes toward the visitor, it found that the ratios of gases were inverted. Instead of water dominating, carbon dioxide overwhelmed the readings, nearly 8 times more abundant than water vapor. Such chemistry was not just unusual, it was unprecedented. The comet seemed to be telling us that its birthplace followed rules unlike anything in our solar system. Perhaps it formed in a region where water could not freeze but carbon dioxide could, a zone of alien thermodynamics around another star. Yet the mystery went deeper. Instruments on Earth and in orbit detected a coma that extended much farther than expected, hundreds of thousands of kilometers wide. How could a nucleus no larger than a small city sustain such a vast envelope of gas? The physics did not add up. If it were shedding material at the predicted rates, it should have crumbled apart. And yet, 3I divided by Atlas remained intact, glowing and persistent as it swept past Mars. Even stranger was the direction of the outgassing. Normally, the solar wind sculpts cometary comas into teardrop shapes, with gas streaming away from the sunday. But in images from both Hubble and ground-based telescopes, portions of the coma seemed to flow sunward, not away. To many observers, this appeared backward, as though the comet was defying the basic rules of solar radiation pressure. Explanations ranged from optical illusions caused by viewing geometry to the possibility of localized jets erupting from its surface at odd angles. None of them fit comfortably. Some researchers proposed that 3I divided by Atlas might not be a solid body at all, but a loose cluster of fragments venting together. Others suggested that its surface chemistry was unique, with insulating layers of organic material trapping water while allowing carbon dioxide to escape freely. Still, others pointed to the role of cosmic rays. Over millions of years in interstellar space, radiation may have altered its ices, creating exotic compounds that vaporized in unfamiliar ways once sunlight returned. For every theory, there was a counter-argument. If it were fragmenting, why did high-resolution images show no obvious pieces? If it were insulated, why did the coma grow so vast? If cosmic rays had processed its ices, why did the chemical ratios look so extreme? The more data we gathered, the more tangled the puzzle became. To call it an enigma was no exaggeration. Outgassing is supposed to be the simplest thing about comets. Ice turns to vapor, vapor escapes, physics explains the rest. With 3I divided by Atlas, that simplicity collapsed. Its activity was too large, too strange, too persistent. Even as it sped past Mars, the readings defied tidy explanations. And perhaps that was the lesson. Outgassing is not just about molecules and sunlight, it is about history. Each comet carries the memory of where it formed, what it endured, and how it has traveled. For a visitor born around another star, the chemistry may reflect conditions we have never seen. The enigma of 3I divided by Atlas was not a flaw in our models, but a reminder that our models are provincial, shaped by one solar system, one set of rules, one limited view. As the data poured in, astronomers admitted something humbling. This comet was unlike any we had imagined. Its gases told a story not of familiarity but of difference, not of reassurance but of mystery. And in the silence of space, as it vented its alien breath near Mars, it left us with the realization that the universe's simplest processes are still full of surprises. For centuries, comets have been described as dirty snowballs. At their core lies a mixture of frozen water, dust, and organic molecules. As they approach the sun, the water awakens first, sublimating into vapor, swelling into vast comas and streaming tails. Water has always been the loudest voice in a comet's song. It dominates their chemistry, sets the scale of their activity, and provides the benchmarks by which astronomers classify them. But when 3I divided by Atlas revealed its spectral fingerprint, that familiar voice was absent. The detectors on the James Webb Space Telescope strained to find the usual water signatures and found almost none. Instead, the readings sang with carbon dioxide. Strong, sharp lines appeared where water should have been. The ratios were inverted. Carbon dioxide outnumbered water by nearly 8-to-1. It was as though the script had been rewritten in a language Earth had never heard. At first, scientists doubted the data. Perhaps the measurements were contaminated by background noise. Perhaps the angle of observation hid the water vapor. But as confirmations poured in from ground-based observatories, from NASA's Swift satellite, from the European Trace Gas Orbiter circling Mars, the picture became undeniable. Water was quiet. Carbon dioxide was loud. This imbalance carried implications as strange as they were profound. In our solar system, such chemistry is rare. Water freezes easily in the cold reaches of the Oort cloud or Kuiper belt, while carbon dioxide usually plays only a supporting role. To find a body dominated by CO2 suggested a birthplace very different from our own. Perhaps 3I divided by Atlas formed closer to its star, in a region too warm for water to condense, but still cold enough for carbon dioxide to freeze. Perhaps it was born in a disk where chemistry tilted toward carbon rather than oxygen. Wherever it came from, its silence on water spoke volumes, and the voice of carbon dioxide was not gentle. Instruments measured a coma stretching nearly 350,000 kilometers across, larger than the distance between Earth and the Moon. For an object only a few kilometers wide, this was astonishing. It was as if the comet's very breath dwarfed its body, spilling into space in a cloud so vast that Mars itself felt its touch. No water-dominated comet in our solar system had ever shown such a scale. The absence of water also sharpened the mystery of survival. Interstellar space is brutal. Radiation and cosmic rays erode ices, break molecules, strip surfaces bare. Water ice, fragile and volatile, is especially vulnerable. If 3I divided by Atlas once carried water, perhaps it had long since been destroyed, leaving behind more resilient stores of carbon dioxide. This would mean that what we saw was not its full history, but the remnant of a journey measured in millions of years. To some, the imbalance raised more speculative questions. If different stars produce different balances of elements, then interstellar comets like 3I divided by Atlas are samples of other chemical worlds. What if water is rare in those systems? What if, across the galaxy, planets form not around oceans but around carbon-rich ices and atmospheres? For astrobiologists, The silence of water in this visitor hinted at alien biochemistries, life that might grow not from the familiar chemistry of Earth, but from exotic pathways written in carbon dioxide and molecules we barely understand. And yet, there was beauty in the paradox. The silence of water did not mean lifelessness. It meant difference. The voice of carbon dioxide reminded us that our solar system is not the template for the universe, only one example among many. The galaxy is wide, and its nurseries diverse. To hear CO2 speak so strongly was to be reminded that worlds may exist whose rules do not resemble ours, whose oceans are not of water, whose skies are not like Earth's. Near Mars, in October 2025, 3I divided by Atlas sang this alien song into the void. Not loud enough for the human ear, not bright enough for the human eye, but clear in the instruments that listened across the gulf. And in its strange melody, we were offered a glimpse of another kind of world, one where water is silent and carbon dioxide carries the voice of creation. Brightness can be deceptive. To the human eye, a star in the night sky looks luminous, but in truth it may be faint and unimaginably distant. With comets, brightness usually tells a simpler story. The size of the nucleus, the activity of its surface, the amount of gas and dust scattering sunlight into space. Bigger comets shine brighter, smaller ones dim. Yet 3I divided by Atlas broke that rule in ways that unsettled astronomers. Early calculations placed its nucleus at no more than a few kilometers across, perhaps 5 at the upper limit, possibly much smaller. By comparison, many solar system comets are 10, 20, even 50 kilometers wide. Based on its estimated size, 3I divided by Atlas should have appeared faint, a blur barely detectable by sensitive telescopes. And yet, from the moment of its discovery, it shone with a luminosity that defied expectation. The glow was not just a matter of the coma reflecting sunlight. Even when instruments corrected for dust and distance, the object remained brighter than models allowed. Something about its composition or structure amplified its presence in the night sky. To the untrained eye, it would have looked like nothing more than a faint star. But to astronomers, that faintness was too bright, too persistent, too inconsistent with the numbers. Several theories arose. One suggested that the surface of 3I divided by Atlas was unusually reflective, coated in fresh ice that had not yet darkened under the bombardment of cosmic rays. Another proposed that fragmentation might be at play, invisible shards orbiting the nucleus, scattering sunlight and making the whole system appear brighter than a single body could. A third possibility focused on the dust grains themselves. If they were unusually small or smooth, they might scatter light more efficiently, creating an optical illusion of brightness disproportionate to the mass being released. But none of these explanations fully satisfied. Reflectivity alone could not account for the scale of the glow. Fragmentation should have revealed distinct peaks in radar or optical data, which were not observed. Dust properties could explain some anomalies, but not the overall persistence of the brightness. It was as if 3I divided by Atlas carried a hidden mechanism, a secret engine for shining, built into its alien chemistry. The brightness mattered because it influenced how we studied the object. Astronomers rely on luminosity to estimate size and activity. If 3I divided by Atlas glowed too strongly, then every measurement derived from brightness became suspect. Was it truly a small nucleus, or was it larger than expected, hidden beneath layers of gas and dust? Was its activity mild, or was it shedding material at extraordinary rates? The uncertainty rippled through every model, every prediction, every attempt to pin down its identity. From Mars' orbit, the glow was particularly striking. Instruments designed to map the planet's surface caught faint overexposures when 3I divided by Atlas passed near the limb of the sky. For a body so small and so far, this was astonishing. It suggested that the red planet had become a silent witness to a spectacle we could not fully explain. A comet-like object, borne around another star, shining too brightly as it raced through the void. Some speculated that the glow might not be entirely natural. They were cautious, careful not to drift into the realm of science fiction, but the thought lingered. Could reflective materials, forged in alien conditions, mimic the properties of engineered surfaces? Could the brightness itself be a kind of message, a signature of a world we will never see? Mainstream science dismissed the idea, but the strangeness of the data ensured that whispers of speculation continued. In the end, the glow of 3I divided by Atlas remained what it always had been, a puzzle. Too bright for its size, too persistent for its chemistry, too strange for easy classification. It was a reminder that light can deceive, that what shines in the night sky is not always what it seems. And as the interstellar wanderer vanished into the distance, its glow became symbolic, a faint but unforgettable beacon of how little we truly know about the debris of other worlds. When radar beams from Earth-based observatories were aimed at 3I divided by Atlas, astronomers expected the usual echoes. Cometary surfaces are notoriously rough, jagged cliffs, fractured ice, porous layers of dust. Their radar signatures typically scatter in chaotic patterns, reflections smeared and noisy. That is what makes comets so difficult to study. They behave like shattered mosaics rather than polished stones. But when the signals returned from 3I divided by Atlas, they carried a surprise. The echoes were smoother than expected, almost mirror-like. To call it a mirror was poetic exaggeration. But the data suggested that the nucleus, or at least portions of it, reflected radio waves with unusual coherence. Instead of breaking the beam into a noisy blur, the surface seemed to bounce it back in patterns that implied broad, flat, or unusually even regions. For a natural body, especially one wandering interstellar space for millions of years, this was strange. Time and radiation usually erode smoothness, pitting ice with craters and fractures. Yet 3I divided by Atlas appeared to carry a skin that gleamed under radar's invisible touch. Speculation followed quickly. One possibility was that cosmic rays had melted and refrozen the outer layers countless times during its long journey, forming a crust of vitrified ice, glass-like, dense, and reflective. Another suggested that sublimation of water long ago had left behind hardened shells of carbon dioxide and organic compounds, compressed into smooth slabs under vacuum conditions. Both explanations were scientifically plausible, yet both stretched the imagination. Could nature truly create surfaces this reflective, this clean, on a body so small? The mirror effect also complicated brightness measurements. If the surface reflected sunlight as coherently as it did radar, that might explain why 3I divided by Atlas glowed more strongly than its size suggested. Smooth ices can act like diffuse mirrors, scattering light efficiently across wide angles. But if so, the nucleus would be unlike any comet nucleus in our solar system, not dark and sooty, but radiant and crisp. That raised deeper questions. Was this smoothness the product of its birthplace or of its passage through interstellar space? Some scientists argued for an origin story tied to alien environments. Around other stars, the chemistry of protoplanetary disks might yield ices with different textures, denser and more cohesive. Instead of the crumbly snowballs we know, such systems might produce compact, crystalline blocks, resistant to erosion, capable of preserving smooth faces over cosmic timescales. In this scenario, 3I divided by Atlas was not unusual. It was representative of a class of interstellar debris we had never seen before. Others allowed themselves a more unsettling thought. Smoothness, after all, is a trait we associate with design. Human engineers polish mirrors, grind lenses, and refine surfaces to control reflection. Could the mirror-like echoes of 3I divided by Atlas hint at something more than nature? The mainstream answer was no. Extraordinary claims require extraordinary evidence, and the data remained well within the realm of natural processes. Still, the whispers persisted. For a moment, scientists and the public alike entertained the thought of an artifact, a shard of something not just interstellar but intentional. Whatever the cause, the radar echoes remained striking. They hinted at a surface that was less chaotic, less broken, more unified than anything expected, and that smoothness carried implications beyond curiosity. If fragments of 3I divided by Atlas ever reached Mars, their reflective properties might alter how dust absorbs heat, how it interacts with the thin atmosphere, even how rovers' instruments perceive the soil. Small effects, perhaps, but reminders that interstellar material is not only exotic, it is interactive. In the end, the mirror effect became another puzzle piece in a growing mosaic of anomalies. 3I divided by Atlas was too fast, too bright, too strange in its chemistry. Now it was also too smooth. Each observation deepened the sense that this was no ordinary comet. It was, instead, a messenger carved by forces we had never fully imagined, polished, perhaps, by the long dark between stars, carrying with it the gleam of another world's story. Long before spacecraft leave Earth, before rovers roll across alien terrain, our first line of planetary defense begins with listening. The Goldstone Deep Space Communications Complex in California, with its massive dish antennas rising from the Mojave Desert, was built to speak with distant probes. Yet it has also become one of Earth's most sensitive ears for cosmic intruders. When 3I divided by Atlas rushed past Mars and sped deeper into the inner solar system, Goldstone turned its beams outward, casting pulses of radio energy into the void and waiting for the whispers that returned. The echoes came faintly, like voices carried on the edge of silence. Radar observations are unforgiving. The signal must travel millions of kilometers, strike a body no larger than a small city, then return across the same gulf to a receiver on Earth. By the time those waves reach the dish, they are billions of times weaker than when they left. Yet within that weakness lies detail: the shape of the nucleus, the texture of the surface, the way an interstellar visitor scatters light in frequencies invisible to human eyes. For 3I divided by Atlas, the whispers told a story that was as unsettling as it was fascinating. The echoes suggested a nucleus smoother than expected, confirming what earlier measurements had hinted. Instead of the jagged, irregular scattering common to comets, the reflections were coherent, as though sliding off wide, flat regions. The mirror effect, as some called it, seemed real. But the whispers carried another surprise: subtle fluctuations in frequency that implied motion, not just the hyperbolic rush of the orbit, but possible rotation of the nucleus itself. Rotation is usually easy to measure. As comets tumble, their changing profiles modulate the radar echoes in predictable ways. Yet 3I divided by Atlas refused to follow the pattern. The fluctuations were there, but faint, inconsistent, as though the object spun too slowly to be measured or too smoothly to produce the expected variation. For weeks, Goldstone's data analysts debated what they were seeing. Was this a body rotating once every few days? Or was it nearly locked, spinning so slowly that one face remained toward the sun for weeks on end? Either possibility carried mysteries. A slow rotator might imply structural stability, unlike fragile solar system comets. A nearly locked nucleus might hint at forces we do not yet understand. There were other whispers, two faint signals that seemed to scatter not from a single body, but from a diffuse region around it. Could the nucleus have been shedding fragments too small to see with telescopes, but large enough to reflect radar? Or was the coma itself so dense with carbon dioxide and dust that it interfered with the returning beams? The answer remained ambiguous, another puzzle added to the growing list. For planetary scientists, these whispers were more than data points. They were a reminder of how tenuous our connection to the cosmos can be. A dish on Earth, a pulse of radio waves, a faint echo across tens of millions of kilometers that was all we had to probe an object older than our world, forged in a nursery of stars beyond our reach. Each return signal was like a heartbeat, telling us that the visitor was real, that it was present, that it was more complex than we imagined. Goldstone's role in the encounter also carried symbolism. It was the same facility that had tracked spacecraft bound for the moon, the same dish that had listened for signals from Voyager as it crossed into interstellar space. Now, it was listening to an interstellar wanderer coming the other way. The symmetry was striking. Humanity's machines venturing outward, and nature's messengers arriving inward, both bridged by the same technology, the same patient ears in the desert. In the end, the radar whispers from Goldstone did not solve the mysteries of 3I divided by Atlas. They could not explain its chemistry, or its speed, or its glow, but they confirmed its strangeness in a way no optical telescope could. They revealed a body that was both smooth and elusive, rotating but not clearly, shedding fragments but unpredictably. They reminded us that sometimes the quietest signals carry the loudest messages. As the comet raced away from Mars and back into the deeper solar system, Goldstone kept listening, straining for echoes until the visitor grew too faint to hear. And when the silence finally came, it left behind a humbling truth. Even with our greatest instruments, the galaxy's wanderers will always speak more in whispers than in words. The James Webb Space Telescope, stationed 1 million miles from Earth at the quiet balance point of Lagrange 2, was designed to peer into the earliest galaxies, to trace starlight stretched thin across cosmic time. But in October 2025, its golden mirrors turned closer to home, focusing not on distant galaxies, but on an interstellar traveler rushing past Mars. 3I divided by Atlas, already a puzzle to every instrument that studied it, now revealed its secrets in the invisible language of heat. Webb's infrared vision does not see light as we do. It senses warmth, the faint glow of molecules as they vibrate and rotate. To Webb, 3I divided by Atlas was not a point of light, but a chemical song. Each wavelength in its spectrum told of a substance boiling away, each peak and dip mapping an inventory of alien ices. The results were as beautiful as they were confusing. Carbon dioxide lines dominated the spectrum, rising like mountains against a flat plain. Water, usually the loudest voice in any comet's composition, was faint, nearly silent. This imbalance had already been hinted at by other instruments, but Webb confirmed it beyond doubt. The comet was breathing carbon dioxide into space at a rate no model had ever predicted, creating a vast envelope that dwarfed the red planet itself. In the data, Mars looked small, the visitor looked enormous, but Webb saw more than chemistry. By analyzing the heat signature of the coma, it estimated the temperature of the escaping gases. They were warmer than expected, suggesting that sublimation was not occurring evenly across the surface. Instead, it seemed to erupt from localized jets, geysers of alien ice boiling away in bursts, scattering dust and gas into asymmetric plumes. These plumes explained the strange shapes seen in optical images. Comas bending toward the sun, tails faint and inconsistent, patterns that defied the textbook diagrams of comet physics. Perhaps the most unsettling feature was the scale of the carbon dioxide cloud. Webb's wide-field instruments traced it outward for hundreds of thousands of kilometers, a halo so vast that it seemed to mock the small nucleus at its core. How could something so tiny power a shroud so immense? One explanation suggested fragmentation, chunks of ice breaking away, each venting independently as they drifted into space. Another pointed to chemistry itself. Perhaps the surface of 3I divided by Atlas was layered, with carbon dioxide locked in pockets that erupted explosively when warmed. Both ideas carried weight, but neither solved the riddle completely. There were smaller mysteries too. In the mid-infrared, Webb detected faint absorption bands consistent with organic compounds, carbon-bearing molecules more complex than simple gases. They were weak, almost hidden in the data, but they were there. If true, this meant that 3I divided by Atlas carried not only alien ices, but also alien organics, materials shaped in another solar system long ago. Their presence did not mean life, but they hinted at chemistry that could someday feed it. To astrobiologists, this was the most tantalizing whisper yet. From its perch far beyond Earth, Webb watched as the comet passed near Mars, its heat signatures rising and falling like the breathing of a restless giant. The data streamed back in terabytes, filling servers with information that scientists would analyze for years. And yet, even in the first results, one truth was clear. 3I divided by Atlas was not ordinary. It was not even close. It was something our solar system had never produced, an ice fragment from a different nursery, carrying the fingerprints of another star's creation. In the silence of space, Webb did what human eyes could not. It saw the heat. It saw the hidden chemistry. It revealed the voice of carbon dioxide, the faint whispers of organics, the strange physics of a comet that glowed brighter, breathed harder, and lasted longer than anyone expected. And as the interstellar wanderer rushed past Mars, Webb gave us not answers, but a sharper, deeper version of the mystery. When humanity built orbiters to circle Mars, the intention was simple: map the surface, study the atmosphere, and search for signs of habitability. Yet, in October 2025, those machines inherited a new role. As 3I divided by Atlas swept through the inner solar system, Mars became an unplanned outpost for interstellar astronomy. For the first time, another planet served as a cosmic observatory, offering a vantage point Earth could never provide. From Earth, the geometry of the encounter was frustrating. During the week surrounding perihelion, 3I divided by Atlas lay too close to the sun in the sky, its faint light drowned in solar glare. Telescopes on our home world and in orbit around it were blinded. But Mars occupied a different position. To orbiters circling the red planet, the interstellar visitor was not hidden by sunlight. The geometry opened a window at the very moment Earth was blind. By sheer cosmic coincidence, Mars became the best seat in the solar system to witness the passage. The Mars Reconnaissance Orbiter took the lead. Its high-rise camera, normally tasked with mapping dunes, landslides, and boulders, turned outward. It caught streaks of light against starry backdrops, the kind of images that later would be stitched together into animations showing the comet's rush past Mars. Though faint, they confirmed details of its trajectory with a precision Earth could not match. Meanwhile, MAVEN, with instruments tuned to measure the upper atmosphere, detected ripples in Mars's ionosphere as the coma of 3I divided by Atlas brushed past. It was not a collision, not even a close call, but the faint hiss of charged particles grazing a planetary atmosphere. For a world with no magnetic shield, the effect was meaningful. It showed how vulnerable Mars remains to cosmic influences, not only to the Sun, but to visitors arriving from interstellar space. The Trace Gas Orbiter, operated by the European Space Agency, made its own contribution. Its spectrometers scanned the high atmosphere and reported faint chemical anomalies, carbon compounds not usually seen in Mars's skies. Whether they were fragments of 3I divided by Atlas itself or artifacts of disturbed dust layers, no one could say for certain. But their timing coincided with the passage, leaving little doubt that Mars had briefly recorded the fingerprint of a galactic wanderer. Together, these orbiters transformed Mars into a kind of relay station for the rest of humanity. They captured a perspective Earth had lost, sending home streams of data that filled the blackout period when our own telescopes could see nothing. In those weeks, Mars was not simply a subject of study. It was a partner, an observatory in its own right. The symbolism was powerful. For decades, we have dreamed of using Mars as a platform for exploration, a place where astronauts might build telescopes free from Earth's atmosphere, where robotic outposts might one day map the stars with clarity unachievable at home. The encounter with 3I divided by Atlas offered a preview of that future. Without intention, Mars played the role of cosmic eye, extending humanity's reach beyond the limits of our home world. And the results were not only scientific, but philosophical. To imagine Mars watching the sky, its orbiters tuned outward rather than downward, was to imagine the planet as something more than a silent desert. It became, for a brief moment, an extension of our curiosity, a witness to an event too fleeting and too distant for Earth to hold. When the data finally reached our scientists, they pieced together the story. An interstellar object racing by, a coma brushing the edge of Mars's atmosphere, faint chemical and electrical disturbances marking its passage. No dramatic collisions, no catastrophic storms. Just a quiet reminder that other worlds, too, can look outward, can record the universe as it unfolds around them. Mars as a cosmic observatory was never part of the plan. Yet, in 2025, it became reality. The red planet turned its instruments skyward, and in doing so, reminded us that the solar system is full of vantage points. Earth is not the only platform for astronomy. Mars had proven that the universe can be observed from many worlds, and sometimes those worlds see what we cannot. Every comet leaves something behind: dust grains, ice crystals, ionized gases, a thin but measurable wake that can stretch for millions of kilometers. In our solar system, Earth sometimes crosses these trails long after a comet has passed, igniting meteor showers that streak across our skies. So when 3I divided by ATLAS swept past Mars in October 2025, scientists asked the natural question: did the interstellar visitor leave a trail of its own? And if it did, what secrets might it hold? The evidence was elusive. Mars orbiters searched their instruments for signs of particulate matter lingering in the upper atmosphere. MAVEN, tuned to detect subtle changes in charged particles, recorded faint disturbances, brief spikes that could have been fragments of dust ionized by solar radiation. The Trace Gas Orbiter noted slight anomalies in carbon dioxide levels, too small to claim as proof, but too well-timed to ignore. Even the Mars Reconnaissance Orbiter, with cameras designed for surface imaging, caught faint streaks against the sky that may have been drifting debris. Yet none of these observations amounted to certainty. The data were suggestive, not definitive, like footprints half erased by wind. One possibility was that 3I divided by Atlas's trail was too diffuse to detect. Unlike typical comets, whose orbits keep them bound to the sun for countless returns, this visitor was a stranger, passing only once. Its ices may have vented violently, scattering dust in chaotic streams rather than well-formed ribbons. If so, Mars might have intersected only the edges of a vast but faint plume, too thin for orbiters to confirm. The planet's thin atmosphere would have made detection even harder, dispersing small grains before they could accumulate. Another possibility was more tantalizing. Perhaps fragments really did fall into Mars's atmosphere, burning faintly as microscopic meteors. Unlike the meteor showers we see from Earth, they would have been invisible to human eyes under Mars's butterscotch skies, producing only subtle flashes too quick for orbiters to catch. Yet those flashes could have seeded the air with exotic compounds, traces of alien chemistry drifting briefly before settling into the soil. For planetary scientists, the prospect was electrifying. If even a handful of grains from 3I divided by Atlas reached the Martian surface, they would represent the first samples of interstellar material delivered to another planet. Somewhere in the regolith, mingled with dust that has lain undisturbed for eons, might lie particles forged around another star, carrying isotopic ratios unlike anything in our solar system. To imagine future astronauts brushing aside sand to find such fragments was to imagine holding a piece of the galaxy in one's hand. Skeptics cautioned restraint. Mars had weathered countless cometary encounters before. Its atmosphere is thin but effective at burning up small particles. Larger fragments from 3I divided by Atlas, if any existed, would likely have missed the planet altogether. The trail may have been there, but too faint, too transient, lost before our orbiters could measure it. To assume more would be to step beyond science into speculation, and yet the timing was difficult to ignore. The small anomalies in particle counts, in chemical ratios, in faint atmospheric ripples all clustered around the hours of closest approach. It was as if Mars itself had felt a brush of something passing, a whisper of alien dust sweeping through its skies. No catastrophe, no visible storm, but a delicate reminder that interstellar travelers do not pass silently. They shed, they scatter, they leave behind traces for those with instruments sensitive enough to listen. So, did 3I divided by Atlas leave a trail? The answer, for now, is both yes and no. Yes, in the sense that it vented gas and dust into space, carving a plume that likely stretched millions of kilometers. Yes, in the sense that orbiters saw hints of disturbances aligned with its passage. But no, in the sense of certainty. No unmistakable fragment was captured. No undeniable meteor flash recorded. The trail remains a suggestion, a shadow, a ghost. And perhaps that is fitting. 3I divided by Atlas was a visitor defined by elusiveness, too fast to chase, too strange to classify, too fleeting to hold. Its trail, like its presence, was real yet intangible. A mark left not on the surface of Mars, but on our imagination, reminding us that every interstellar traveler carries not only mysteries, but also the quiet promise of evidence just out of reach. In October 2025, no human stood on Mars to witness the passage of 3I divided by Atlas. The red planet was still silent then, watched only by robotic eyes and orbiting machines. Yet it is not difficult to imagine another timeline, a future where human colonists had already claimed the deserts of Mars, building habitats in its valleys and cities beneath transparent domes. What would they have seen that night, looking upward into the alien sky? The Martian sky is unlike Earth's. By day, it glows pale butterscotch, filtered through dust and a thin, carbon dioxide-rich atmosphere. By night, it turns almost black, with stars shining sharper and steadier than anywhere on Earth. The thin air scatters little light, and the absence of moisture leaves the heavens crisp and vast. Against this backdrop, 3I divided by Atlas would have appeared not as a spectacular streak like the comets of old, but as a faint, fast-moving glow, a traveler from another star whispering across the firmament. Imagine a settlement perched on the rim of Gale Crater. Colonists step outside their pressurized habitats in suits, their helmets reflecting the faint light of Phobos, Mars's small inner moon. They tilt their heads back to see a new star gliding across the sky, brighter than the constellations but dimmer than the moon. Its movement detectable not over hours but over minutes. For those trained in astronomy, it would be a revelation. The third confirmed interstellar object, passing not near Earth but near their adopted home. For others, it would be something more visceral awe, unease, perhaps even fear. Children might press their gloved hands against the transparent walls of observation domes, asking questions no parent could easily answer. Where did it come from? Will it hit us? Does it carry life? Does it carry life? In the silence of Mars, answers would come slowly, filtered through radio transmissions from Earth and the cautious voices of scientists. Yet even without full explanations, the experience itself would leave an imprint. To stand on another world and watch a visitor from beyond the stars pass overhead is to feel both profoundly small and profoundly connected. The encounter would also shape culture. Just as ancient civilizations on Earth wove comets into myth, Martian settlers would craft their own stories. 3 divided by Atlas might be remembered as a sign, a reminder that Mars is not isolated, that it too belongs to a universe alive with motion. Poems would be written, songs composed, murals painted inside domes where dust storms raged outside. A fragment of interstellar history would become part of Martian folklore. For scientists on Mars, the opportunities would be immense. Instruments stationed on the surface could have gathered data Earth-based observatories missed. Spectrometers might have captured the faint trail of dust particles settling into the thin air. Meteor detectors could have recorded microscopic flashes as grains from the coma burned high in the sky. Samples collected from the soil afterward might have contained the first tangible pieces of another solar system, delivered not to Earth, but to Mars. And yet, alongside excitement, there would be unease. In an environment already hostile to human life, the possibility of contamination, chemical or biological, would not be dismissed lightly. Would alien molecules poison the fragile attempts at terraforming? Could interstellar organics interact with Martian dust in unexpected ways? The settlers would watch not only with wonder but with caution, knowing that their survival depended on understanding what drifted through their skies. Though purely hypothetical, this vision of Martian skywatchers reminds us of what is at stake. One day, humans will stand on Mars, and when they do, the universe will not pause. Visitors like 3 divided by Atlas will come again, and next time there may be eyes to see them directly, hearts to feel their passage, and hands to collect the fragments they leave behind. For now, it remains an imagined future, a story told in what-ifs. But in that imagination lies inspiration. To picture colonists looking up at an interstellar comet is to glimpse the destiny of exploration itself. Humanity scattered across worlds, watching the galaxy together, writing new myths beneath alien skies. Mars has always lived in the shadow of silence. Its atmosphere is less than 1% as dense as Earth's, too thin to carry sound in any familiar way, too fragile to shield the planet from the impact of meteors. And yet, when 3 divided by Atlas swept past in October 2025, scientists wondered if even this faint veil of gas might have felt the brush of its passage. Could an interstellar visitor, racing at over 200,000 kilometers per hour, send shock waves through a sky so tenuous it barely exists? The data whispered possibilities. Instruments aboard Maven detected subtle fluctuations in the ionosphere, the charged upper layer of the Martian atmosphere. For a few hours, density readings spiked, then fell, as though disturbed by an unseen tide. It was not a storm, not a collision, but something gentler, the faint pulse of energy from the comet's coma sweeping across Mars like the passing of a ghost. On Earth, shock waves are familiar. They ripple from explosions, sonic booms, and meteors burning through thick skies. They roar, they crack, they shatter windows. On Mars, the same phenomenon would be different. The thin air cannot carry a roar. Instead, it would manifest as a pressure ripple, silent to the human ear but visible to instruments tuned to measure the smallest shifts. To stand on the Martian surface during such an event would not be to hear a sound, but perhaps to feel a faint vibration in one's suit, a whisper of movement too delicate to name. The idea that 3 divided by Atlas could stir shock waves at all speaks to the scale of its coma. Carbon dioxide vented from its surface expanded into a cloud hundreds of thousands of kilometers wide. Even at a distance of 29 million kilometers from Mars, Streams of particles and radiation brushed the planet's edge. In the fragile balance of the Martian atmosphere, even such faint inputs could register as disturbances. What would be lost in Earth's thick sky became detectable in Mars's thin one. The implications extended beyond curiosity. For decades, scientists have debated how Mars lost its ancient oceans. Without a magnetic field, the solar wind strips its atmosphere relentlessly, molecule by molecule. But encounters with interstellar visitors like 3I divided by Atlas add another layer to the story. Each passing comet brings with it energy, particles, perhaps even shock waves that stir and erode what little air remains. Over billions of years, such encounters might have been countless, each one a small, quiet theft, contributing to the planet's long transformation from blue world to desert. Some researchers speculated further. If shockwaves truly rippled through the Martian sky, might they leave lasting effects? Could they alter the distribution of dust in the atmosphere, shifting storm patterns for weeks afterward? Could they compress and then relax the ionosphere in ways that affect how Mars interacts with solar radiation? These were not idle questions. For future explorers, the stability of the Martian atmosphere will matter for communications, for climate control, for survival itself. Understanding how it responds to cosmic encounters is more than an academic exercise. And yet, there is something poetic in the thought of shockwaves on Mars, a planet known for its silence, touched by ripples from a visitor born around another star. No thunder rolled across its valleys, no winds howled through its canyons. Instead, the disturbance was quiet, delicate, measurable only by machines. But silence does not mean insignificance. In those faint pulses lay a story of connection, a reminder that even the most tenuous air is part of the larger dance of the cosmos. As 3I divided by Atlas receded into the dark, Mars returned to stillness. The fluctuations faded, the atmosphere settled, the dust storms resumed their usual patterns. Nothing seemed changed, and yet everything had. For a brief moment, a thin sky had carried the imprint of a galaxy-spanning journey. The shockwaves were gone, but the memory remained, etched into data streams and human imagination alike. Every comet carries the fingerprint of its birthplace. The mixture of ices and dust locked into its nucleus is a record of the temperatures, pressures, and chemistry of the region where it first formed. In our solar system, comets from the Oort cloud or Kuiper belt are dominated by water ice, with smaller fractions of carbon monoxide, carbon dioxide, and organics. That pattern has shaped our understanding for decades. But 3I divided by Atlas broke the mold. Its chemistry inverted expectations. Carbon dioxide dominated while water was strangely muted. To explain this, scientists turned to theories of formation and began to imagine entire worlds that followed rules unlike our own. The most straightforward explanation invokes the idea of a carbon dioxide snow line. In a protoplanetary disk, gases condense into ices at different distances from the star, depending on temperature. Far out, water freezes easily. Closer in, water vapor dominates and carbon dioxide begins to condense. If 3I divided by Atlas formed in such a zone too warm for water ice, but cold enough for carbon dioxide, then its strange chemistry would make sense. It would be a shard from a region where CO2, not water, was the building block of icy worlds. In our solar system, that region would lie near the asteroid belt. But around another star, the distances and conditions could be very different. Another theory points to stellar diversity. Not every star burns like our Sunday cooler red dwarfs, and hotter, brighter stars each shape their disks in unique ways. Around a dim star, the carbon dioxide snowline might lie far closer in, creating broad regions rich in CO2 ice. Around a hotter star, unusual chemical reactions might favor carbon-rich compounds over oxygen-rich ones. In such environments, comets like 3I divided by Atlas could be the rule rather than the exception. What seems exotic to us might be normal elsewhere. Cosmic rays offer another piece of the puzzle. During millions of years adrift in interstellar space, high-energy particles bombard comets, altering their chemistry. Water ice is particularly vulnerable to this kind of radiation, breaking down into hydrogen and oxygen that may escape into space. Carbon dioxide, on the other hand, can survive such processing more readily. Over eons, this imbalance could transform the outer layers of an interstellar body, erasing much of its water and leaving a crust dominated by CO2. If true, then 3I divided by Atlas was not born carbon dioxide rich, but became so through the slow alchemy of radiation and time. A more speculative hypothesis imagines fragmentation and selective survival. Perhaps 3I divided by Atlas is not a whole comet at all, but a piece of a larger body. When its parent world, shattered by gravitational encounters or violent impacts, fragments with different chemistries may have been ejected. Some pieces rich in water may not have survived the rigors of interstellar travel, sublimating into nothingness. Others, like 3I divided by Atlas, carried more durable ices and endured. In this view, the comet is not a representative of a typical planet-forming zone, but a survivor, a relic of destruction and survival. The implications of these theories stretch far beyond one visitor. If carbon dioxide-dominated comets are common in other star systems, then the galaxy may be filled with worlds whose chemistry is very different from Earth's. Planets in those systems might not build oceans of water, but atmospheres thick with carbon dioxide, seas of frozen carbon, or even cycles of weather, unlike anything we have seen. For astrobiology, this expands the canvas of possibility. Life may not always depend on water. It may emerge in ways that make sense only under carbon-rich skies. For now, the truth remains hidden within the faint coma of 3I divided by Atlas. Did it form in a carbon dioxide world, in a disk where water never froze? Was it sculpted by radiation, or born from destruction? We may never know. But the very act of asking the question widens our perspective. It reminds us that our solar system is not the blueprint for the cosmos. It is one example among many. And in the glow of 3I divided by Atlas, enriched in carbon dioxide, we glimpse the diversity of worlds beyond our Sunday. Most scientists are careful with their words. The moment speculation drifts too far into the extraordinary, reputations are at stake. Yet, when 3I divided by Atlas revealed its strange behavior in 2025, its brightness too high for its size, its smooth radar echoes, its dominance of carbon dioxide over water, some could not help but ask the question that always lingers in the background. What if it was not natural at all? The thought was not unprecedented. When the first interstellar visitor, Oumuamua, appeared in 2017, its cigar-like shape and unexplained acceleration triggered a wave of speculation. Was it a fragment of rock or the relic of a spacecraft? Harvard astronomer Avi Loeb famously suggested it could be alien technology, perhaps a solar sail or a probe. The idea was controversial, even ridiculed, but it set a precedent. Interstellar objects, by their very nature, invite our imaginations to reach further than evidence allows. With 3I divided by Atlas, the clues seemed to whisper in the same direction. The mirror-like radar reflections, more coherent than expected, resembled engineered surfaces rather than natural ice. The brightness, stronger than its size predicted, could have been explained by high reflectivity, the kind of property one might design deliberately. And the inverted chemistry, dominated by carbon dioxide instead of water, was so strange that some wondered if it was not a chemical accident but a signal of intent. Could it have been a shard of something larger, a fragment of alien construction wandering the galaxy long after its makers were gone? Could it have been a sliver of a vessel, its original purpose lost to time, reduced to drifting debris? The very thought turns scientific caution into mythic imagination. Yet, in a sense, that is what astronomy has always done: turned faint lights into stories of origin and purpose. Mainstream explanations remained grounded in physics. Smooth radar echoes could come from vitrified ice crusts, hardened over millions of years. High brightness could result from reflective carbon ices. Exotic chemistry could be the byproduct of radiation processing during its interstellar voyage. None of these required intelligence, only time and the indifference of the cosmos. Still, the coincidences stacked uneasily. Why so smooth? Why so bright? Why so different from every comet we had ever seen? Speculation grew louder among the public. Headlines toyed with the possibility of alien artifacts. Forums debated whether 3I divided by Atlas was natural or engineered. To most scientists, the idea remained improbable, but they also acknowledged an uncomfortable truth. With only brief windows of observation and faint data, definitive answers were out of reach. The mysteries could not be explained fully. In the absence of certainty, imagination thrives. Philosophers of science pointed out that even if 3I divided by Atlas were artificial, we might never be able to prove it. Interstellar debris arrives without context, stripped of history, its makers, if they exist, lost beyond light years. What would an engineered shard look like after millions of years in space? Would it not resemble rock and ice, weathered by radiation, softened by time? To distinguish artifact from natural fragment might be impossible. And perhaps that was the most humbling realization: that alien engineering, if it exists, could hide in plain sight, indistinguishable from nature. In the end, scientists continued to treat 3I divided by Atlas as natural until proven otherwise. It was safer, more rigorous, more consistent with the evidence, but the speculation refused to die, and perhaps it never should. To ask whether a strange visitor might be artificial is not to abandon science, but to admit curiosity to keep open the possibility that the universe holds not only unfamiliar chemistry, but unfamiliar minds. So, was 3I divided by Atlas a shard of alien engineering? Probably not, but in its brightness, in its smoothness, in its silence on water and voice of carbon dioxide, it carried just enough strangeness to stir the question. And that question, unanswered, may be its greatest legacy. For sometimes, the most terrifying possibility is not what we know, but what we cannot rule out. In less than a decade, humanity witnessed 3 visitors from beyond the stars. Each appeared suddenly, uninvited, carrying with it the mystery of another world. 1I, Oumuamua in 2017. 2I divided by Borisov in 2019. And finally, in 2025, 3I divided by Atlas. Together, they form a trilogy of interstellar encounters, 3 case studies in cosmic diversity, 3 reminders of how little we know about the galaxy's debris. The first, Oumuamua, was the quietest yet the loudest in its implications. Detected as a faint, elongated object racing away from the sun, it showed no coma, no outgassing, no visible activity. By all appearances, it was inert, a dry shard of something larger, and yet its motion betrayed a secret. As it left the solar system, it accelerated slightly, as though pushed by an unseen hand. No gas or dust was visible to explain it. This contradiction, asteroid-like in form, comet-like in behavior, made Oumuamua a riddle. It forced scientists to imagine exotic explanations, from hydrogen ice sublimating invisibly to radiation pressure acting on an unusually thin, reflective surface. For some, it even opened the door to speculation about alien technology. 2 years later, Borisov arrived. Unlike Oumuamua, it looked familiar. It grew a bright coma and a long tail, behaving much like the comets of our own solar system. Its activity was strong and steady, shedding water vapor, dust, and gas in the ways astronomers had modeled for decades. Yet, even Borisov carried strangeness. Its chemistry was unusual, an excess of carbon monoxide that dwarfed any comet known to us. To produce such ratios, it must have formed in an environment colder than the Kuiper Belt, perhaps in the deep freeze of a distant star's outskirts. Borisov reassured us with its cometary behavior, but challenged us with its alien chemistry. Then came 3I divided by Atlas, the most perplexing of all. It combined the contradictions of Oumuamua with the activity of Borisov, yet refused to align neatly with either. Its coma bloomed vast and bright, but its chemistry was inverted, dominated by carbon dioxide, with water strangely muted. Radar revealed smooth surfaces, reflecting like mirrors rather than scattering like rubble. Its brightness outshone its size, and its outgassing patterns defied expectations. Where Oumuamua had been silent and Borisov familiar, Atlas was both loud and alien, behaving like a comet yet singing in a register no comet should. Comparing the three is like comparing 3 voices from a distant choir. Oumuamua hummed quietly, leaving behind a puzzle of motion. Borisov sang clearly, but in a key unfamiliar to us. Atlas shouted, its voice strange and distorted, louder than expected. Together, they suggest that the galaxy's population of wandering fragments is far more diverse than we imagined. The contrasts extend beyond chemistry. Oumuamua was small, perhaps only a few hundred meters long, shaped like a cigar or a pancake, depending on interpretation. Borisov's nucleus was closer to half a kilometer across, a sturdy fragment behaving as expected. Atlas seemed larger, but its exact size remained elusive, hidden by the immensity of its coma. Each visitor revealed not only different origins, but different scales of survival. The timing, too, carried meaning. Oumuamua was discovered only after it had already passed perihelion, racing away before telescopes could prepare. Borisov arrived with more warning, giving scientists months to observe. Atlas offered the richest opportunity yet discovered while still inbound, tracked across its close encounter with Mars, and studied by an unprecedented array of instruments, from Earth's telescopes to Martian orbiters. The progression felt almost scripted, as if the universe were gradually revealing the complexity of interstellar debris in stages. And yet, even with 3 examples, certainty remains elusive. Do these objects represent the true diversity of interstellar material, or are they outliers, chosen by chance and bias in our detection methods? Are there countless others, quieter and stranger, passing unnoticed because our instruments are not yet sharp enough? Oumuamua, Borisov, and Atlas form a gallery of difference. The silent shard, the carbon monoxide comet, the carbon dioxide enigma. Each tells a story of a different birthplace, a different star, a different chemistry. Taken together, they whisper of a galaxy alive with variety, where no 2 systems produce debris alike. For humanity, these 3 are more than curiosities. They are reminders that the solar system is open, porous, touched by fragments of other worlds. Each visitor is a sample of elsewhere, a time capsule from alien nurseries. And if 3 objects in less than a decade have been so radically different, then what wonders and what terrors await discovery when the next interstellar stranger arrives? When 3I divided by Atlas appeared in 2025, it marked the 3rd time in less than a decade that humanity had detected an interstellar visitor. Before 2017, no such object had ever been confirmed. Then came Oumuamua, racing through the inner solar system in silence. 2 years later, Borisov, glowing with a familiar but alien chemistry. And now, Atlas, louder, stranger, brighter. 3 arrivals in quick succession, after billions of years of emptiness. For astronomers, the question arose naturally. Were these encounters cosmic coincidences or signs of a deeper pattern? One argument leans toward coincidence. After all, the galaxy has always been full of wandering debris. Every star system produces it. During the violent early years of planet formation, countless fragments are ejected into interstellar space, flung outward by giant planets or by gravitational dances too chaotic to resolve. These objects drift endlessly, scattered like pollen across the Milky Way. Statistically, trillions must exist. The fact that a few happen to pass close enough for us to notice may simply be chance. But another explanation lies closer to home. Our technology finally became sharp enough to see them. Before the 2010 seconds, surveys of the sky were less comprehensive. Many small, fast-moving objects likely slipped past undetected, lost in the noise of asteroids and comets. With the rise of wide-field telescopes like Pan-STARRS, Atlas, and the Zwicky Transient Facility, our ability to scan the heavens improved dramatically. Each new survey increased the odds of discovery. Perhaps interstellar visitors were always there, quietly passing, and we only just gained the eyes to notice. Still, the rapid sequence of discoveries felt almost deliberate. Oumuamua in 2017, Borisov in 2019, Atlas in 2025, 3 arrivals in less than 10 years, after billions of years of none. Could there be rhythms in the galaxy, waves of debris sweeping through our neighborhood as the sun orbits the Milky Way? Some researchers speculated that the solar system might occasionally cross streams of interstellar fragments, ejected long ago from star clusters. Like Earth passing through a meteor shower, perhaps our system was moving through a galactic current rich in wandering ice and rock. Others noted the diversity of the objects. Oumuamua was dry, silent, tumbling strangely. Borisov was wet and active, but chemically exotic. Atlas was carbon dioxide rich, glowing too brightly, shedding a coma vast beyond reason. To have 3 so different, so quickly, seemed less like random sampling and more like a hint. Perhaps we were glimpsing the true diversity of interstellar debris, not rare exceptions, but common varieties of a population far more varied than our theories predicted. If so, then the pattern is not just in timing, but in meaning. Each visitor revealed something the others did not. Oumuamua challenged our models of motion. Borisov expanded our chemistry. Atlas overturned both size and activity. Together, they formed not a coincidence, but a progression, each adding to the puzzle of how planetary systems form and evolve. There is also the human tendency to see patterns where none exist. Our minds crave narratives, arcs, and connections. 3 arrivals in close succession tempt us to weave a story of cosmic intent, as though the galaxy had chosen this decade to reveal its messengers. But perhaps this is projection, born from the awe of finally noticing what was always happening. Whether coincidence or pattern, the lesson is the same. Interstellar objects are not myths. They are real, frequent enough to be seen, and strange enough to challenge every assumption we hold. If we have seen 3 in less than 10 years, the odds suggest many more will come, some brighter, some darker, some carrying chemistries we cannot yet imagine. So, are we witnessing randomness, or are we seeing the edge of a hidden rhythm in the galaxy? For now, we cannot say. But whether chance or pattern, the message of 3 I divided by Atlas remains clear. We are not isolated. Our solar system is not sealed. It is open to the galaxy, brushed now and then by visitors whose arrivals remind us that the cosmos is alive with motion, and that even coincidences can feel like destiny when they pass so close. And then, it was gone. The interstellar traveler that had unsettled our models, whispered across Mars's skies, and ignited so many questions, slipped quietly back into the dark. 3. Divided by Atlas, the third wanderer ever caught by human eyes, had rushed past at impossible speed, leaving us not with answers but with echoes. Its glow faded. Its carbon dioxide coma stretched thin and dispersed. Its trail, if any, dissolved into the solar wind. Mars returned to its silence, its storms once again shaped only by dust, sun, and thin air. But for us, the silence after the fireball was anything but empty. It was charged with wonder. For months, we had pointed every telescope, every orbiter, every instrument at this visitor. We had measured gases, tracked its orbit, strained to detect fragments. We had asked if it was natural or artificial, ordinary or extraordinary, a shard of chaos or a relic of design. And when it vanished beyond Jupiter's orbit, we were left with something rarer than certainty: humility. The questions remain. Why did it shine so brightly for its size? Why did its chemistry sing in carbon dioxide instead of water? Why did radar beams return smooth, mirror-like echoes from a body that should have been jagged and scarred? Each anomaly felt like a piece of a puzzle, but the picture never formed. 3, divided by Atlas, passed too quickly, leaving the image forever incomplete. From Earth, the mystery grew even sharper. Our best observatories were blinded during its closest approach, hidden in the sun's glare. For weeks, the story of the interstellar wanderer unfolded not in our skies, but in those of Mars. The red planet, the world we dream of colonizing, the world we project our futures onto, became the accidental witness of something cosmic. That irony will linger. Mars saw what Earth could not, and yet, maybe this is fitting. Interstellar objects are reminders that we do not control the stage. We are not the audience of choice. We are not the destination. These fragments pass where they will, brushing past planets, grazing atmospheres, leaving faint shadows in data streams. We catch them when chance allows, and then we let them go. Their stories are not ours to finish. The silence after 3 divided by Atlas is not the silence of absence, but the silence of perspective. We are left to reflect, to imagine Mars's thin skies rippling with alien particles, to picture the faint glow against a butterscotch horizon, seen perhaps one day by colonists who will build myths around such visitations, to wonder how many other fragments cross our system unnoticed, too faint, too fast for us to see. In that silence lies a message. Our solar system is not a closed bubble. It is part of a galactic sea, stirred by currents we cannot chart, visited by travelers we barely glimpse. Each one carries the memory of another star, another time, another chemistry. Oumuamua gave us motion without a voice. Borisov gave us activity but alien chemistry. Atlas gave us both, and in doing so, unsettled us most of all. So now, as you rest and let your thoughts drift, remember that the sky above you is not only ours. It is open. It is porous. It is alive with strangers passing in the dark. And sometimes, one comes close enough to brush a world we know, close enough to terrify us with its speed and its strangeness, close enough to remind us how fragile our understanding really is. The fireball has faded, the echoes are gone, but the silence it leaves behind still speaks. It tells us that the galaxy is vast, that its stories are endless, and that we have only just begun to listen.